So now that we've had a few practice with means, let's look at practice with sampling with proportions. So again, when we're dealing with proportions, we're dealing with data that is using percentages, proportions or percentages. So on all of our last examples, we were dealing with means, and means means an average of something. Here, we're looking at proportions, or the percentage of time that something happens. So just like before, if I have the population proportion, we call that P, and the sample proportion is P hat, and that just helps us to keep track of which one's which. Kind of like before, I had the mean, and then I had the mean of the sample. It's the same idea, but here we're calling the mean of the sample P hat. The standard deviation of my sample, it has to be found using P. So the standard deviation of sample proportions is taking P times Q divided by N. Remember, what's Q? Q is just 1 minus P. So if I tell you that P is 0.2, then that means Q must be 0.8. And then P hat would be what I actually observed, which will probably be something close to 0.2, but not exactly. And again, what we're doing is we're looking at finding the proportion of something over several samples. So the process that I will go through is almost identical to the process I just went through with means. This is proportions, so let's talk about what's the same and what's different. I'm still checking randomization, I'm still checking 10%, I'm still checking independence, but now I'm checking success fail. And that means I have to have 10 successes and 10 failures. And again, how do I know successes and failures? I might have to take N times P and N times Q, and that would give me the number of success and the number failure, because again, it's just the number of trials times the percentage of success, or it might just be given to me in the question. Again, we're dealing with the normal model, so we're finding a z-score. Notice what I'm doing though is I'm finding observed, which is P hat, minus expected, which is P, over the standard deviation. So all of this is the standard deviation of my sample, which is square root of PQ over N. So they're not going to give me a standard deviation, I have to compute it. Remember, drawing a picture is optional but recommended, and then we'll state our conclusion. So let's take a look at an example together. In this one, we're saying groovy M&Ms are supposed to make up 30% of the candies sold. In a large bag of 250 M&Ms, what is the probability that we get at least 25% groovy? So again, before I even check conditions or anything, not a bad idea to say, hey, guess what? This is P. This is what I'm expecting to have happen, is I'm expecting 30% of candies to be groovy. 250 is my N, that's the number of trials because I'm going to be checking those M&Ms. And at least 25% is going to be the P hat, that's going to be my observed, or the value that I'm checking. And at least means that I'm going to want my value to be greater than or equal to 0.25. But let's go ahead and look at our first steps then, which would be check the conditions. And again, this is a proportions question because we're given a percentage, not an average, but a percentage. What percent are groovy? Random, we can assume M&Ms are put into bags randomly, so in the factory they're obviously all mixed up and randomly put into bags. 10%, 250 M&Ms is less than 10% of all M&Ms, thank God. Independence, because of the high sample size, colors of M&Ms are independent, so a lot of people struggle with that independence. In this case, because N is so large, because there are so many M&Ms, that when I pull out one M&M, the probability is going to change so small that it's going to basically be independent enough. And then success fail, N times P is 250, which is N times P, which is 30%, 0.3. That was 75, and Q also greater than 10, and so success fail condition is met. And because the conditions are met, I will use a normal model, 0.3, comma, and then this is the standard deviation. So this is just the work for the standard deviation. I've separated them with a comma because this is the mean. And again, then I just did this work, and this work resulted in 0.029. So the mean is going to be 0.3, and the standard deviation is going to be 0.029. And I suppose instead of mu, I should be using x bar for the mean of the sample. Then we're going to draw a picture. I'm looking at least probability. Remember, at least is greater than or equal to. So I'm expecting 30%. My question is, what is the probability I get 25% or more? So just looking at this picture, I know I should get at least a 50% probability. So next I'm going to perform the calculations. The calculations are to find the z-score, and z, remember, is observed. That's p hat minus expected. So this is p hat minus p over PQ over N. Now notice I didn't show any work down here. Why didn't I? Because on the other screen just a moment ago, I did all of the work to find 0.029. So if you do all of the work to find 0.029, there's no reason to reproduce the work here. Then I get a z-score of negative 1.724, and notice that's what I'm entering into StatCrunch in my standard normal calculator with a mean of 0 and a standard deviation of 1. I'm writing my probability notation that says the probability that p hat is greater than or equal to 0.25 is equal to the probability that z is greater than or equal to negative 1.724, and notice that high probability, well over 50%. So I feel pretty confident that I'm going to get at least 25% groovy candies. And then again, when I write my solution, notice I've written, instead of 0.9576, I've just written it as a percentage. So let's take a look at another example that's maybe not quite as much fun because there's no M&Ms involved. This is dealing with voting on the upcoming school budget. Very important. So we don't know it yet, but 52% of voters plan to vote yes on the upcoming school budget. That is P. We poll a random sample of 300 voters. What might the percentage of yes voters appear to be in our poll? 300 is N. So that's the only two values that I get. So you might be saying, well, hold up. On the last question, we had a P and we had a P hat. Notice, because I'm dealing with the empirical rule, I'm not looking for testing a certain value. I'm saying 52% plan to vote yes. That's in the population. So in our sample of 300, how many might we expect to see? So first thing I would do is check my conditions. And again, this is proportions question because I'm giving a percent, not an average. So random, voters were selected randomly. 10%, 300 is less than 10% of all voters. Did I just make that up? Kind of. So I could say 300 is less than 10% of all voters if at least 3,000 vote, because honestly, I don't know how big this district is. We're not given that information. Independence, voters' opinions are independent of one another, and success fail, N times P is greater than or equal to 10, N times Q is greater than or equal to 10. Since they both are, now I can say, because the conditions are met, I'll use a normal model. And again, what's my normal model? Well, P is 0.52 because that was given to me in the question. The standard deviation needs to be calculated, and that standard deviation is 0.0288, which I found by taking PQ over N and then taking the square root. So again, order of operations is important. But here's the normal model I will use moving forward. So now, because it's an empirical rule question, I'm just going to be drawing a picture. And when I draw the picture, I start with my 0.52 here in the middle, and then that standard deviation that I came up with on the other page is how I'm going to add to get these values and subtract to get these values. So I'm not using any other number besides what I found when I took 0.52 times 0.48, which was 100 minus 52, divided by 300 and the square root. And again, I've already shown you how you can cheat by using StatCrunch, and notice I'm going to get those same answers again using my standard deviation, which was found by taking the square root of PQ over N, which was P is 0.52, Q is 1 minus 0.52, which was the 0.48, and N was 300 voters. So I do all of that, and then I take the square root of the answer, and that is where 0.0288 came from. And then as I write my conclusion, which I will never actually make you write for an assessment, then I would say, according to the normal model, I expect 68% of samples of 300 voters to have between 49.1 and 54.9 yes votes, 95% of the time between 46.2% and 57.8% of yes votes, and 99.7% of the time between 43.3 and 60.7% yes votes. And just for funsies, let's look at one more example. Example 3, dealing with proportions. Again, about 3% of fortune cookies on average, so don't get thrown off by average. 3% is a proportion, and that's how I know this is a proportions question, are shipped without a fortune. How sad is that when you get Chinese food and you don't get a fortune? In a bag of 1,000 cookies, what is the probability that no more than 2%? So this is P, because that's the whole population. 3% of fortune cookies are shipped without a fortune. I'm trying to find the probability that no more than 2%. 2% is going to be my P hat. And when I'm actually finding my z-score, it says no more than 2%, so it's going to be less than or equal to 0.02. So keep that in mind. But first, let's check conditions. This is a proportions question since we're given a percentage, so I'm going to check random. It doesn't say random, so how do I get around that? Well, I'm going to assume, just like with M&Ms, that fortunes are put into the bags randomly. 10%, 1,000 is less than 10% of all fortune cookies made. I feel pretty confident in that fact since there is probably 1,000 in my local Chinese shop right now. Independence, whether a cookie has a fortune is independent of other cookies in the bag. And success fail, N times P, N times Q, both are at least 10, so we're good to go. What are my calculations? I don't have to calculate P. It's given to me in the question, 3%. I do have to calculate the standard deviation. Remember, if P is 0.3, then Q is 1 minus 0.03, which is 0.97. So that's where I got 0.03, 0.97 divided by 1,000. And that gave me a standard deviation of 0.0054. That is the model that I'm going to use to find my z-score, to plug it into StatCrunch, etc. So now that I've done all of the work, I'm going to actually perform the calculations now. Remember, I'm using my z-score formula, which is my observed minus expected over the standard deviation, which is the PQ over N. I did all of this on the last page, and I found that number to be 0.0054, which is why you don't see me showing that work again here. I'm just copying it over. P hat is my observed, that's the 2%. Expected is 3%. When I subtract and divide, I get negative 1.852. I use that number here in StatCrunch to find my probability, and notice that because it said no more than 2%, I looked for less than or equal to. So the probability that P hat is less than or equal to 0.02 is the probability that Z is less than or equal to negative 1.852, and that is the probability that I came up with. And my conclusion, according to the normal model, the probability that no more than 2% of fortune cookies don't contain fortunes is 3.2%.